What if I told you time hasn't always existed? Before the Big Bang, there was no past, no future, no ticking clock. Because time only begins when change begins. When the universe started expanding, change started happening. And that's when time was born. But here's the real question. If time had a beginning, can it also be bent? Can we travel through it? According to Albert Einstein and his theory of general relativity, time is not fixed. Move close to the speed of light, and time slows down. Enter extreme gravity, and time bends. So maybe time travel to the future is possible. But traveling to the past, that might break reality itself. Today, we're going to explore whether time travel is science or just science fiction. So first, let's understand something very important. What is time? Time is not something you can see or touch. It's not a physical object. Time is simply the measurement of change. When something changes, we say time has passed. When the Earth rotates, we call it a day. When it revolves around the sun, we call it a year. Every clock you've ever seen is just measuring change. Now think about this carefully. If absolutely nothing changes and no movement, no motion, no energy shift, would time still have any meaning? According to modern cosmology, before the Big Bang, the universe was not expanding. It was compressed into an extremely dense singular state. There were no stars, no galaxies, no motion as we understand it today. And here's the key idea. If there is no change, there is nothing to measure. If there is nothing to measure, time has no meaning. That's why many physicists argue that time itself began at the moment of the Big Bang, because that is when expansion started. That is when change began. The universe began expanding, matter formed, energy started transforming, galaxies began moving apart, and from that ongoing change, time emerged. Even today, scientists say the universe is still expanding. And as long as expansion continues, change continues. And as long as change continues, time exists. So in a very deep sense, time is not something separate from the universe. Time is the story of change itself. Now here's where things become even more fascinating. If time is connected to change, and change is connected to the universe itself, then time is not something fixed or universal. It might actually depend on conditions. This is exactly what Albert Einstein proposed in his theory of general relativity. Einstein showed that time is not separate from space. Together, they form something called space-time. And space-time is flexible, it can stretch, it can bend. This means time does not flow at the same rate everywhere. For example, if a person travels extremely fast, close to the speed of light, time for that person slows down compared to someone standing still on Earth. This effect is called time dilation. Imagine this scenario. An astronaut travels in a spaceship at nearly the speed of light for what feels like 1 year to him. But back on Earth, 10 or even 20 years pass. When he returns, he hasn't aged much, but everyone on Earth has grown older. He didn't feel time stopping. For him, everything felt normal. But compared to Earth, he has moved forward into the future. This isn't science fiction. It's a real prediction of relativity, and parts of it have already been experimentally confirmed. So traveling to the future is not fantasy. It's physics, but traveling to the past, that's where reality begins to break down. But now comes the most dangerous question. Can we travel to the past? At first it sounds exciting. Fix your mistakes, see history, change events. But the moment you think carefully, reality starts collapsing. One of the most famous problems is the grandfather paradox. Imagine this. You build a time machine and travel back in time. While you're there, you accidentally prevent your grandfather from meeting your grandmother. If they never meet, your father is never born. If your father is never born, you are never born. If you were never born, then who went back in time? This creates a logical contradiction. The cause destroys its own effect. The timeline collapses. And this is not the only issue. There are other logical problems too, like causal loops, where an event becomes its own cause, or paradoxes where information appears from nowhere without an origin. These contradictions challenge the very foundation of logic and causality. Physics struggles with past time travel because our current understanding of the universe is built on cause and effect. The past creates the present. The present creates the future. If you allow the future to change the past, the chain of causality breaks. Even in advanced theories of space-time, solutions that allow backward time travel often require extreme and unrealistic conditions, like exotic matter with negative energy, which has never been observed in a usable form. So while traveling to the future fits naturally within relativity, traveling to the past creates paradoxes that physics still cannot resolve. So we've seen that traveling to the future is possible through speed or gravity. But why does time always seem to flow in one direction, from past to future? The answer lies in entropy, a measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in the universe. In other words, natural processes move from order to disorder. A broken glass never spontaneously reassembles. Ice cubes melt in a warm drink, but water never magically freezes back in place on its own. This increase in entropy gives time its direction. Physicists call this the arrow of time. It's why we remember the past but cannot remember the future, because the past had lower entropy, and the future has higher entropy. Even if you could travel at near light speed or be near a black hole, entropy still moves forward. That's why while the future is accessible through time dilation, the past remains fundamentally blocked. If somehow entropy could decrease, the universe becoming more ordered, then theoretically time could reverse. But that would require conditions completely unlike anything in reality. It's practically impossible. In Interstellar, not only does gravity slow time near Gargantua, but the movie also hints at the irreversible flow of events. Even with relativity, the past cannot be changed. Entropy explains why time moves forward naturally. It sets the universal one-way street for time, allowing future travel under physics laws, but preventing backward travel to the past. So far, we've seen how speed and entropy affect time. But there's another powerful factor: gravity. According to Einstein's general relativity, massive objects like stars, planets, and especially black holes bend space-time. The stronger the gravitational field, the slower time moves. Imagine standing near a black hole. Seconds for you might stretch into years for someone far away. This is called gravitational time dilation, and it's a real effect, not just theoretical. Even here on Earth, this happens subtly. GPS satellites experience time slightly faster than clocks on the surface because gravity is weaker up there. Engineers must correct for this difference, or GPS would become inaccurate within minutes. In the movie Interstellar, the planet near the black hole Gargantua is a perfect demonstration. 1 hour on that planet equals 7 years on Earth. The astronauts live through minutes, but back home decades pass. That's gravity bending time itself. This shows us two incredible things. First, future time travel is scientifically plausible. Second, the past remains blocked. Nature's laws, combined with entropy and causality, prevent us from undoing events. Time is not fixed. It's flexible, stretching and bending with the universe, speed and gravity. And that's the amazing reality of our universe. Time is both real and relative, guiding our journey from past to future, but always keeping the past out of reach.